So now I want to talk about graphs and charts. In the last section, we talked about frequency tables, relative frequency tables, and cumulative frequency tables. Now we want to talk about some other ways to display our data that's not in a table. So we're going to talk about four main types of graphs. So I'm going to talk about a histogram and a relative frequency histogram. Those are for quantitative data. I'm going to talk about bar graphs, that's used for qualitative data. I'm going to talk about pie charts, which can be for quantitative or qualitative data, but it's usually qualitative. And I'm going to talk about a stem and leaf plot. So here's a histogram. A histogram is a bar graph for quantitative data. The bars have a natural order and must be attached at the bar, so they have to be touching one another. The bar widths have a specific meaning. The wider the bar, the more the height in this case. So it consists of continuous adjoining bars. Our x-axis is the classes, and our y-axis is the frequency or relative frequency. Whether I use the frequency or relative frequency, that's the information we got from our tables in section 2.2, our shape is going to be the same, and that's a really important thing to remember. I don't know why they represented this with a caterpillar, though. One advantage to histograms is that they can display really large data sets, okay? The rule of thumb is that to use a histogram, if you have continuous data, you must have like 100 values or more. That's like the best way to use a histogram. So along our horizontal axis, sometimes we use our lower class limits, or sometimes we use midpoints to label. Just make sure that your x-axis and y-axis are always labeled. So here we have our frequency. Here we have our class boundaries. This is going back to the bison in PowerPoint 2. Remember, it's just the weights of bison would have been a better title for this graph. You want to label your class boundaries. So these were the boundaries between each of the classes, and the frequency with that occurred. So here is our frequency. Here's our standard histogram. You always want to make sure that you have a descriptive title and your axis is labeled clearly, and never use 3D or other fancy effects. It makes it a lot easier for your data to be read and understood if it's a little simpler. Sometimes class limits are easier to read than midpoints, so you know the weights that are in each bar. So why don't we construct a histogram? This table contains the pulse rate of 40 female nurses. Let's construct a histogram of this data. So I am going to come up with a nice title. We'll just say pulse rates of nurses. My x-axis is going to be pulse rates. My y-axis is going to be frequency. Maybe I'll change colors once I label my bins. So I'm going to have 60 to 69, 70 to 79, 80 to 89, 90 to 99. Make this bigger. 100 to 109, 110 to 119. Oh, I have to make this a lot bigger. Okay, and 120 to 129. And I'm trying to make these each the same width, but as I'm sketching this out myself, I'm not doing the best job. And then we need our frequencies. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There we go. So why don't we go ahead and make this graph. I'm going to graph them in. Let's pick a different color. Blue. Okay, so from 60 to 69, I have a frequency of 12. So I go up to 12 and I make my bar. From 70 to 79, I have a frequency of 14. From 80 to 89, I have a frequency of 11. From 90 to 99, I have a frequency of 1. I also have a frequency of 1 from 100 to 109. I have nothing for 110 to 119, and that's okay. Then I have a frequency of 1 over here, but it should be a little bit shorter. So there we have constructed a histogram for the pulse rates of nurses. A relative frequency histogram has the same shape as a histogram, except instead of our y-axis containing the frequencies, it's going to have the relative frequencies. So here we have that our y-axis is now our relative frequency, but the graph still looks the same. And we have to make sure that all the rules for good graphs still apply. We've got a good title. We've got a good title. We've labeled our axes, and we can clearly tell all the information we need from this graph. Bar graphs is like a histogram, but it's for qualitative data, and the qualitative data will go along the x-axis. Along our vertical axis, you could put frequencies or relative frequencies. Again, the graphs will have the same shape. The difference between a bar graph and a histogram, though, is that none of the bars touch, okay? And that's to represent that the classes are not continuous, right? Like if we were graphing the number of M&Ms in a bag, right? We wouldn't want red touching blue, right? We have to show that the number of red M&Ms is different than the number of blue M&Ms is different than the number of green M&Ms. Okay? So, in our bison example, the weights flowed from one category to the next, but that doesn't happen with bar graphs. Okay? Also, the order of the bars doesn't matter, though they're often organized from largest frequency to smallest frequency. But how confusing would that be for like weights, right? Weights already have an order to them, so be really careful. So here's a bar graph example. So 4 fast food restaurants are located on a busy corner in St. Louis. The restaurants are Whitney's, McDonald's, Burger King, and Jack in the Box. These are the number of regular hamburgers each sold during lunchtime on January 2nd. 150, 200, 175 and 120 respectively. That means we had Wendy's, McDonald's, Burger King, and Jack in the Box. Notice how the number of hamburgers sold can't really flow from one to the other. Okay, there's no natural ordering of these restaurants, although I'm a big Wendy's fan. But that's because this data is not numerical, right? It's a frequency of something qualitative. So you have to make sure you're clear in your comparison, because we're comparing the number of hamburgers, not whether or not you think Wendy's, McDonald's, or Burger King or Jack in the Box is the best. So the number of hamburgers sold by McDonald's and McDonald's are two different things. The number of hamburgers sold is just one of the characteristics of McDonald's, but just stating McDonald's could mean the number of employees, hours open per week, etc. So make sure you're being specific. So be clear. So here we have our qualitative variable, which is our Wendy's, McDonald's, Burger King, or Jack in the Box, and we have our quantitative variable, which is the number of hamburgers sold. So I would arrange these in orders from largest to smallest on our bar graph, seeing how there's a space, right, to represent that these do not flow continuously. A bison could gain or lose weight and move between the classes, but the gap here represents the fact that a burger at McDonald's can't gradually change into a Burger King burger. That'd be really silly. In a pie chart, each category is depicted as a slice of pie, okay? The larger the slice, the larger the relative frequency. We use relative frequencies for these. Making the slice is simple because there's 360 degrees in a circle. In case you didn't know that, 360 degrees. If I was to go all the way around a circle. So if the relative frequency class is 0.2, that class gets 20% of the 360 degree circle. So let me try and guesstimate, like 20%. Well, that's like a fifth. So it'd be a lot bigger, right? 0.2 or 20%. Just an estimate. So the entire pie represents 100%. So here we have people's favorite type of movie. Comedy, sci-fi, drama, romance, or action, right? Divided up into an example of a pie chart. So we could take the number of hamburgers sold at Wendy's, McDonald's, Burger King, and Jack in the Box, calculate their relative frequencies by dividing by our total sample size, and then we would get these relative frequencies. That don't really add up to 1. Shame on me. But these should add up to 1. Change that to 23.3. And that fixes everything. So then they get that many degrees of pi. I took 2333 times 360 degrees, and that gave me 83 degrees. I took 0.31 times 360 degrees. That gave me 112 degrees, and so on and so forth. So here we have our beautiful, beautiful pie chart. Again, we want to make sure everything is well labeled. The last thing I want to talk about is a stem and leaf plot. It looks like a histogram. It's faster to draw than a histogram, and the classes or the stems of a stem plot are given to you. You use the first digit of all your quantitative data, because remember this is only for quantitative data, as the stems. And you can get more flexibility of rounding the data so that the final digit after rounding is suitable as a leaf. And it actually displays the values. Whereas opposed to when you had frequencies, we don't know the actual weights, for example, of those bison, because they were not expressed. They were kind of all clumped together. Stem plots don't work well with large data sets like a histogram does, so that's something to keep in mind. So to make a stem plot, you need to separate each observation into a stem. That's the final but rightmost digit. The leaf, which is the final digit. And stems can have as many digits as needed. But each leaf can only contain a single digit. Single meaning 1. We write the stems in a vertical column with the smallest at the top. We draw a vertical line to the right of this column. And we write out each leaf in the row to the right of its stem in increasing order out from the stem. So, here's this data of test scores. The stem will consist of the first digit, which in this case is the tens digit, so we'll have 9, 8, 7, 6 as our stems, because I don't see any other stems that aren't repeated. And to the right, we'll have our leaves. We label these in green. All of these will be our leaves, and we will repeat them multiple times if they happen to occur multiple times. So here we have 62, 69. These are our stems. These are our leaves. And as you can see, because the score of 92 and 93 occurred twice, we did list those 2s and each of those 3s twice. Same thing with a score of 81. So from this, you can see the test scores, and you can see that most students scored 90% or above. Note that the leaves are listed in ascending order with no commas between each leaf. And each plot should always contain a legend so that the reader understands the setup. Here's another example of a stem and leaf plot from quiz scores of students. Note if you have numbers like 2, 2, 3, and 7, but you also have 11 and 20, you can have a stem of 0, and that's okay. But what if I wanted to compare side by side stem and leaf data to compare two data sets. So here's a science class's first quiz scores. And here are their final quiz scores. Okay? I can make a side-by-side stem and leaf plot. So I have scores on first quiz, scores on last quiz, and we can see that more students got 20s, which is, this is a quiz out of 20, than originally, and we don't have any more grades like 2s. Okay? So our students did improve over the course of the semester. So let's create a stem and leaf plot for the following data set. Let's just say these are ages of students, ages of people on a bus. Okay? It's nice to know what data you're studying, so let's figure that. Ages of people on the bus. So I've got my stem, I've got my leaves. My stems are going to be 1 and 2. And my leaves, if I start out with a leaf of 1, I'm going to have a 1, a 3, a 4, a 5, and an 8. Notice I'm not separating these with commas or anything like that. And we do go from smallest to largest. Now I look at 20, I have ooh. There we go. Sorry, I got my iPad under control. We have a leaf of 0, 2, 3, 7, let's make that look like a 2, and 9. So here's our stem and leaf plot. I also need to have a legend, 1, 3 means, let's make these ones look like actual ones for clarity. 1, 3 means 13. So, if the first two classes of frequency distribution are 0 to 9 and 10 to 19, what's the class width? We take 10 minus 0, we get 10. The first two classes of a frequency distribution are 0 to 9 and 10 to 19. What are the class boundaries of the first class? The boundaries between 9 and 10, that's going to be 9.5. If I look at the original 27 values of a data set, can they be identified by knowing 27 is the frequency for 0 to 9? No, we can't know the original values when it comes to frequency data. For number 4, what values are represented by the first row of a stem plot? Well, that's going to be 52, 52, and 59. We're going to skip this question because I did not cover that. Sorry, gang. True, false. A histogram and a relative frequency histogram constructed from the same data will always have the same basic shape, but the vertical scales are different. That's true. They're going to have same shape, but the vertical scale for one's going to be frequency, and for the other it's going to be relative frequency.